So, good afternoon, everyone. It's a pleasure to be here with my colleague. I'm Hamid, and
Ajay. Good afternoon, beautiful people.
we are from Advanced Research Lab of Navinfo Europe in Netherlands, in Eindhoven. And first of all, it's good to be back after a long period of no conferences and nothing. This is my first conference after the COVID. It's great to see people face to face again. We are presenting this tutorial, which we call it Challenges and Obstacles Towards Deploying Deep Learning Models on Mobile Devices. This is an industry challenge and also an issue that many even top companies and top tier AI companies are dealing with. We want to provide some hints on what are the issues that we are having, and also some of the solutions that we have deployed internally, and we come up with some solutions in order to solve some of the issues, but it's a broad topic. We are not covering everything here. So with this, I think Ajay can start with the introduction.
Just a little bit before we jump into the context. The big picture, why we came onto this is what is Navinfo doing by itself. Navinfo is an autonomous driving, a computer vision for autonomous driving company. That's what we do in Europe. But in general, as a whole, Navinfo makes maps. So it's like Here Maps or any other map company. That's how it started, and it's a big player in China. So now when we jump into this company's activities that we are trying to give vision to autonomous driving, let's see what happens and what are the problems we face in everyday life. So what we know is deep learning is a very fast-paced research zone. Let's say tons of papers come out every now and then. So today, if you look at, maybe there's a new paper or even a bunch of new papers which promise a lot of new things with more accuracy, more speed, whatnot, more predictability, for example. So there's a lot more coming out every day. So that space is growing. Now, simultaneously, when we look at the hardware space of what can support these AI models in them, that space is also growing. So when I started this project out in, let's say, 1.5 years back, I didn't even see a few players in this market of hardware that, or at least they were, of course, making it internally, but we didn't know that that's going to be available in the market later. So there are a bunch of new hardware devices that can support AI. So that bubble is also growing. So let's see, this bubble is growing, this bubble is growing, but the guy in the middle trying to bridge these two bubbles, this guy is not growing. So the throughput from this guy to mobile devices is having a problem here. There's a bottleneck here. That's what we are trying to solve. So let's make this space a little bigger. Ideally, to make it seamless, that's what we would want to do. So let's move research to deployment with, let's see with what we are trying to dive into. So the agenda for this talk would be, let's get some background on deep learning. What's deep learning? What are the models? What are they capable of? How to play around with them? How does typically the training process and deployment process happen? And then we talk about this problem statement in a little more detail. And we propose solutions that we have tried and tested in our labs. And we can also continue discussing of what more we could do. And then we would like to add a little bit of our flavor to this, what we do in the lab about model optimization. Of course, we are doing some things in real time when it comes to autonomous driving. So optimizations help, and then we'll have a small pre-recorded demo there, and we'll show you how this works. So, a little bit of background on deep learning. What's deep learning? It's a little confusing terminology to me. When I started, I heard machine learning, which was a buzzword, deep learning another buzzword, and AI another buzzword. So deep learning is a subset of AI. AI is a huge cloud. Is a subset of AI that helps computer to learn from its experience. So that's a very simple introduction I'm giving. Disclaimer, it's just not that it, but what is an experience? So we know deep learning, we've identified experience. And what's an experience? An experience, simply put, is a recording. So if I go meet a person, that's an experience. What is happening is the activity, and what's the response is the ground truth. So if I go meet, let's say, this madam in front of me, so I say hello, that's an experience. So the experience with the ground truth. What is a ground truth? Is it a meeting? Is it a fight? Or what is it? So that's let's say a ground truth. It depends on what we want to identify this activity as. So that is a ground truth. We need what is the activity and the ground truth for our models to train. See, what is training? Training is fitting a curve. So let's say we have 0, 0, 10, 5, or whatever. We fit a curve through it. That's what is training. So we need that ground truth and that event from an experience to do this training. Using a model. What is a model? Model is a graph. It's a sequence of functions within them, and that function is helping us to generalize to, let's say we've seen 100 different samples. The 101st sample, that we should be able to predict. So that's what is called generalization, predict with a good accuracy, and it should scale. So that's what a model does. A deep learning model is a graph that understands the world. So it's a sequence of functions that is capable of generalizing things. Applications of deep learning. The first one from my zone is self-driving cars, what we do in the company. So why do we need deep learning? So if you get inside your car, get the steering wheel on your hands, you just know when to take a left, when to take a right, when to stop, when to accelerate, when to do whatever you want, cruise control or whatever. But for a machine, if you try to explain this, it's very difficult. So think about the process that's going on in your head. When you find a pedestrian in front of you, you will think if the person is about to cross, is he going to stay back? Is he going to run? Is he going to step one time front and then again back? So all this goes on your head. But for a model, if you want to explain as a programmer, let's say, a simple program would be if he's trying to cross, else, if he's trying to cross, stop, else move forward, say, for example. It's not going to be that simple. That's why deep learning comes. And such complicated problems have been well handled by deep learning, let's say. So that's why these applications come here. Automation robots is the same case. Let's say an industrial car maker, for example, needs to have a robot hand picking up from screws to doors of the car, let's say. So these things differ in size, shape, brittlety, let's say, how it can break. So these things have to be understood by one model or a few deep learning models for us to make that work in that field. So fraud detection, somebody is doing credit card, debit card, for example, you've tried to book a flight here, come tap it and just book the flight. Maybe your card is being accessed by somebody else. So this is happening by every bank. This is happening in the behind the screens of every bank. So there, deep learning is again another savior. For healthcare, cancer recognition, there have been cases where some doctors have not really predicted that this is going to happen or cancer is in there. So there have been cases that I have personally seen. So it's quite complicated even for humans. So let's try to make this work with deep learning. So that's another idea why this started. And then chatbots, we need somebody else talking to us, just like humans. So it's another complicated problem. And recommender systems, your YouTube videos, Netflix, Spotify. text recognition, our handwriting, somebody else needs to understand. So all of these are complicated applications. So we need some complicated system that we can get a hold of to do all these things. That's why we go to deep learning for this. And I hand it over to Hamid to take it on from here.
Thank you. So before I continue, I would like to ask if any of you have any questions, feel free to ask. So we are expecting this session to be more interactive. We don't want to just talk and leave the questions for the end. Of course, whenever you have anything unclear, just let us know. Well, with the introduction, we continue with the training of a deep learning model. Actually, we have a couple of steps on how to train a deep learning. Thank you. So the first step is the data collection and preparation. So the models, the deep learning models, will be trained on a specific data sets. I'm not going to the very details of how every single approaches or what is going to be done in this specific process, but it is just to be mentioned that when we are collecting or we plan to train a model, it is very important that the model needs to be trained on a proper data set in order to get the accuracy. By means of proper data set, the data set should be rich enough to capture the complexity of the problem that we want to solve actually. And then once the data is enough for training a model, there will be a series of just calculations iterating over this data set and then make the model train. There are lots of ways in order to prepare the data. Sometimes our data is not enough because the problem is complex. I remember like 2 years ago we have started a project with European Space Agency that actually the main issue there was that we had very limited source of images which were captured by satellites, and the collection of such images were very expensive for the European Space Agency and NASA. So they tried to somehow augment the data by creating fake data, which is very similar to that actually data set. And then from the model's point of view, that data just looks quite homogeneous and very, very similar, regardless of what is the actual data, what is the fake data, which is augmented or created. So that is a very, very important step. The annotation of the data, for instance, imagine we want to train a model for object detection, and then the model needs to learn what is, for instance, a car. So this data as a raw data set, which is just a collection of images, for instance, has to go through a step of data annotation. So someone either in an automated process or by a human involved in the loop, we just mark what is the human, what is a car, what is another object, for instance, and then this information will be embedded in the data set so that the model knows, okay, this is the human, and it tries to learn the features of what is a human, what is a car, what is a bicycle. So this is an important step also towards preparing the proper data set. Then, of course, once we have the data set, it's very important that depending on the task and the problem that we are going to solve, how we are going to design the architecture of a model based on the requirements that we have. So usually we have a model like it is now composed of tens or even hundreds of layers. This is not, I would say, a very, very specific rule for that, but based on the experience and what has been done before by the deep learning scientists and engineers, there is some predicted rule, like for instance, for this specific problem, we are going to use this kind of architecture, maybe with just later some minor modifications, but we need this number of layers, we need to have some convolution layers, deconvolution layers, some other layers involved. So this is all going to be in the process of designing the architecture of the model. Then once we have this mathematics and everything specified, the model has to be implemented somewhere. So now this is also a very important thing because we will focus on that later on in the session. Usually deep learning scientists and engineers, they use a series of deep learning frameworks, which they are just offering a very simplified API and syntaxes in order to develop their model. So they don't have to implement every single thing themselves. They just have predefined functions and libraries that they just can tune and provide and set some parameters, which makes the design and the development of the deep learning models much faster. Then we will start training the model using usually a powerful device like GPUs, or if the model is very large, with a cluster of GPUs, or specific accelerators, like for instance the tensor processing unit of Google or something like that. We will iterate over the data set that we have, and then we will observe that the model is training. Actually, this is the next phase, which the engineer that trains the model actually tracks the training process, and every time that the process is going on, they will check with a separate validation set to see how the accuracy of the model is improving, and if needed, they are doing some adjustments or modifications to the model. So this is the next step where we fine-tune the model parameters because the overall goal is usually to improve the accuracy as much as possible. And once we have modified something, we go back again to the beginning of the process, and then this loop continues until we reach to a point that we are satisfied with the behavior of the model, and then we can test the trained model with a test data set. Usually the test data set is something that is also unseen before by the model, which is considered as a new data set. We can see how the model behaves on something that is not used for the training of the model. So this is all a very simplified way of doing the training. Of course, we have a lot of complexities in any of these steps, which for now we just skip just to give a brief background on this. And then now we continue with the deep learning frameworks. So we mentioned that the development and implementations of deep learning models are usually done by deep learning models, by deep learning frameworks. Now we have put like a couple of, you see that we have a couple of deep learning frameworks which are quite famous. We have CNTK from Microsoft, we have Caffe before, and now we have Caffe 2, we have PyTorch, we have TensorFlow from Google, we have Keras, which is also based on TensorFlow, we have Theano and some other things. So, but mostly, for instance, people are using Keras, PyTorch, TensorFlow, which are the mostly used nowadays. What they are offering is that you have a very simplified API and lots of features that overall tries to simplify how your model is going to be trained. So the main purpose is that they want to simplify everything. So simplicity is one of the main objectives for having a deep learning framework. Also, they are actually, by simplifying the development of deep learning models, they try to facilitate the R&D of the deep learning. Then they are offering very high efficiency and scalability for multiple machines, because they have underneath of their high-level API lots of highly optimized libraries implemented for a specific hardware that they are supporting. For instance, let's say they are supporting a variety of Nvidia GPUs, but the Nvidia GPUs have different architectures, have different number of hardware parameters, like number of streaming multiprocessors, the whether they have, for instance, in the latest architectures, they have int8 support, or they don't have, or they have FP16, or they have Nvidia MPS, or a lot of other these things. We will also discuss about this kind of optimization later in the presentation. Also, they are providing a cleaner interface and also an easy environment to use by the researchers and also engineers. They try to facilitate the exchange of data with the external libraries and providing interoperability and flexibility. The last thing is that some of these deep learning frameworks, they try to highly optimize, as I said, the performance for different hardware. Not all of them, they are offering this, or they are offering for every hardware, but usually this is the case, especially for the ones that they target platforms like Nvidia architecture. They usually implement things based on the highly optimized libraries of Nvidia, so that the performance is quite improved, and also the utilization of the hardware is increased as much as possible. So, as an example, we have PyTorch, which is just one of the widely used neural networks. We just took a video recording of a very simple example of PyTorch. Actually, you have to define the neural network and the parameters, and then you will see that it is only a couple of lines when you import the PyTorch library in Python, and then you define your class with your parameters and your function, and then in maybe less than 20-30 lines you can have a model specified, and also you start training by just calling a function. And that is something that if you as a developer want to do from the beginning, even not considering the optimized way of doing this for the hardware, it can be very complicated. So this is the type of simplicity that we are talking about. So there are lots of, fortunately, code and examples and tutorials for this domain. This is one of the very good advantages of deep learning nowadays. This, what Ajay said about that, we have a huge flow of coming research every day, and lots of publications in different domains, everything improvements. It's very difficult, especially for research, to catch up all the latest work. But on the other hand, we have a lot of things open source. We have a lot of documents, material, libraries, frameworks. Everything is accessible for everyone, and that is a very great opportunity for at least for beginners. So now, after discussing about the deep learning frameworks, we move towards the hardware that is going to be running this process. So we have the CPUs, which is the well-known architectures, have been there for decades, and we have, of course, different ISAs, instruction set architectures like ARM, we have x86, we have now RISC-V, which is emerging and it's getting very popular. We have other architectures as well. We have, apart from the ISA, we have mobile and high-performance CPUs. But it turns out that for capturing the complexity of the recent deep learning models, a CPU is far behind to satisfy the requirements that we have for deep learning models. That's why we are using, in fact, GPUs as because they were introduced as graphic processing units, but now probably the most use of GPUs are for deep learning and for training and inference of deep learning models. We have different vendors and different architectures, but mostly we have Nvidia and also AMD on the other side. Nvidia has its own, I would say, programming language, which is CUDA, while AMD usually uses OpenCL. We have different architectures of GPUs, different sizes of the GPUs depending on the use case. The mobiles now also come with GPUs. We have mobile GPUs which are still powerful enough compared to the power and also the restrictions that we have in a mobile device. But on the other side, we have very high-end and powerful GPUs. We have also GPU clusters like the DGX or the feature that we can simply orchestrate lots of GPUs together, and this is offered by companies like Nvidia that people can use in order to train and run very sophisticated models and deep learning frameworks. We have FPGAs, of course, which are less common compared to the GPUs, but relatively they are more efficient. But we have also the problem of not being that much flexible compared to the other two, like the CPUs or the GPUs, but they are relatively much more efficient. And if we are looking for much more efficiency, we have ASICs, which now can be simply found in any chip which we are having. The ASICs are designed with specific purposes for some specific tasks, and of course we have lots of efficiency and also being more power efficient, but it comes with a lack of programmability and also flexibility in order to program them. The latest type of hardware that we can mention is the quantum devices, which I would say this is something mostly on the research side rather than to be in the industry for now, but there won't be any surprise if they come very soon into the market. So now let's see, we have different deep learning frameworks here, and you see that, for instance, most of them, they are supporting x86 CPU. Again, this is the TensorFlow, this is the TensorFlow Lite, which is mostly developed with the purpose of mobile devices. We have PyTorch and PyTorch Mobile. We have Tencent from a Chinese company. Tencent TNN, Mini DNN is also from another company. We have Caffe, we have a specific deep learning framework from Apple, which is called CoreML. We have TensorRT, which is, well, not a deep learning library, but it's I would say it's an optimization library for Nvidia devices. We have Apache TVM again for optimizing, and also Xiaomi framework. You see that we have support for most of them regarding the x86, but when it comes to ARM CPUs, for instance, TensorFlow doesn't support that. Still, some of them support GPUs with CUDA, and also more of them support OpenCL. We have some APUs, which is, I forgot what it stands for.
AI processing unit.
Oh yeah, AI processing unit, and you see that only, for instance, the Mini DNN and the Xiaomi supports that. There are some processors or SoCs which they are including the APU, like the G90 mobile processor, which has an integrated APU. But you see that if we want to program that or launch something on that, which is actually specifically designed for deep learning, we cannot use any of these frameworks. And we only have to use the Mini DNN or the Xiaomi. The same for the Nvidia deep learning accelerators, which is again an integrated accelerator specifically designed, so this is called Nvidia Deep Learning Accelerators, and it is already included in all the architectures after the Xavier architecture, which was introduced, I think, in 2018. So all the system on chips include the NVDLAs, but they can be only accessed and programmed through TensorRT. We have the NPU, again, another type of processing unit, which is only, again, programmable through the Tencent TNN. We have some specific ASICs for other companies. We have FPGAs, which you see that, for instance, Café is supporting some kind of FPGAs, or the Apache TVM. So the whole point here is that if we develop something with TensorFlow, for instance, and we want to run it for ARM or for APU or for NVDLA, we will have a problem. This is the main issue. Not everything from this series of deep learning frameworks can support whatever architecture that we have in mind. So with this, now Ajay will explain the problem in more detail.
Great. So, yeah, go ahead.
I have one question on the previous slide. I was wondering, are you considering any TPU in the hardware that you consider for learning?
Well, the TPU, well, we didn't include this here. Actually, this is from a preprint we published on Archive. The reason that we didn't consider the TPU is that, as far as we know, TPU is not accessible to outside world. So it is only accessible through Google Cloud Platform. But the others, I mean, the other devices, I mean, it is something that you can use. But for instance, if you subscribe to the Google Cloud Platform, you can subscribe to having TPUs, and then the price will be higher, and then you definitely get a faster output, which I think Ajay will cover about these kind of things, the costs. And
Yeah, sure.
So what are the specific ASICs in this column?
So as I said, we have a variety of ASICs nowadays integrated in different chips. For instance, we have, even in a simple Intel processor, we probably have more than 20 ASICs, which, for instance, for the audio decoding, video decoding, for many different things. And I think these are for different kind of platforms that they have somehow a deep learning accelerator. By any means, one of these frameworks will cover some of them. So for instance, Apple already has a deep learning accelerator, but it is programmable through its Apple Core ML. The same with the, I don't know, Xiaomi or with the Qualcomm system on chips and so on. Yeah.
Yeah. So, are there any more? Great. So to answer that, which is within my reach, is a TPU. We haven't put it here because it's not typically an edge device kind of processing unit. So all these things you find here can be somehow or the other put on an edge device. So you can have a CPU there, you can have a GPU, you can have the other processing units in a small device, or comparatively. So you don't have to go for the cloud. That's one ideal situation that most of the makers want to have. So not going to the cloud. Yes. Okay. So now we come back to this problem statement that we had in the beginning, right? So I don't know how many of you guys have experienced this yet. If you want to try and deploy a network for a particular task, let's say object detection or segmentation or classification or whatever, The frameworks that were mentioned before, they have a tutorial to do that. So they make you go through a series of steps, and they help you deploy something like MobileNet v1. So what has happened meanwhile in this field is we've had MobileNet v2, we've had MobileNet v3, and we've had many different variants coming out of MobileNet, let's say. That's just one example. Take YOLO. YOLO is v1, v2, v3, v4, v5, v6. Within every generation, we've had multiple subsets to accommodate various needs. But why is that we see tutorials or examples showing how to use v1 or v2 when there's several other versions that are out which can outperform its predecessors? That's because when you develop this deep learning model and you try to get it there, you're still not there. And then you come back, you change some things about your model so that it runs on the mobile device, like shown in the previous table, that it does not support this framework, it does not support this device, it does not support many other things. So it comes back to deep learning researchers, and what they have to do is compromise on what's the capability of deep learning networks by replacing them with several other things. So this is what usually happens. And then when that is set right, it goes even further, but still not there. And then we have to come all the way back. This juggling has been going on in my experience as well, and then a few other friends of mine, and I've inquired, and it's a prevalent thing in the industry that I feel. So now so that being the problem, we will now talk about what deployment actually is, what are the steps involved in it, and then let's see what are specific scenarios that we have come across to do this, to understand this. So first, research and development. So you identify, let's say, for example, MobileNet v3 is good for my problem space. It's fast, it's accurate, it's small, it's whatever. Or you found another model, let's say YOLO is very good for me, YOLO v5. So that's this space. You find out different models, and then you build on top of them, so you don't have to do everything from scratch. That's why you have research open. So you start from there. YOLO v5 is good, but then I need to know what part of the architecture gives me what bottleneck, and then I build on top of that and create a beautiful new architecture. Then from there, we have to train that architecture. So we fine-tune the architecture to suit our data set. It could be very different from the one that the initial purpose was. It could be, for example, trained on faces or human beings or tables, chairs, and something. But then you put it to roads. Let's say you need to tune it on cars, cycles, motorcyclists, pedestrians. So you need to fine tune. That's the second stage. And then this is the core part of deployment, where the model was moving here and there, is converting these models into an executable. So this is pretty critical. So when you try and make that an executable for a particular platform through a particular framework, what happens is sometimes the versioning issues happen. So the platform you started with and the platform you ended with, they are very different. So they have different versions in them. That is a very big problem that I never expected before starting this. Secondly, some of them are not even supported. So for example, TensorFlow would today come up with a new layer to support their own paper. They have XYZ v1. And then TensorFlow and their core team would have come up with this architecture to be very fast, very accurate. XYZ v1 will not have support in TensorFlow Lite, for example. So that's the kind of pace that we are talking about when we are at the framework of research and then framework of deployment. TensorFlow is research, and then Lite is deployment framework. So where we start, it's so quick that you get something now, and then where we end, it's not yet there. So that's the problem when you try to convert it into an executable. We'll come to that point shortly. And next, then we still need to have a pipeline that we can run with this executable. So when the engine is ready, you cannot drive your car. So you need the framework around it. So you need wheels, you need the body of the car, you need brakes, you need everything. So in this sense, what it means is you need to have a pipeline to load images. You need to have a pipeline to directly connect to the streaming of the video, for example. And then after detecting it or segmenting it, whatever, you need to be able to give the feed to your cyber physical system to say, okay, now you have to slow it down. Now you have to lock your right segment of wheels. Left segment of wheels can keep rolling. So something like this when it comes to an emergency or whatever. So these kind of things come from the pipeline, not just from the executable model that we developed. So this whole environment has to be developed. Okay, now let's come to one core problem. For example, PyTorch had like a lot of versions. Let's start from V1. V1 until V9 is maybe in a span of 3 years, a little more than that maybe. So in a span of 3 years, so many versions. What does it mean to us is if I had developed a particular model that's very good like a year back, and now I try and port it to an executable, try to convert it to an executable with PyTorch 1.9. I developed with 1.2, try porting it with 1.9, it throws a tantrum. So it says this is not available, that is not available, apart from the code itself, apart from say the syntax which has changed, some of the things within the model itself would have changed by that time. So this we have to address for all these versions. Then if we move, this is a unified model definition. So on an X is like the translator. So if I'm talking in English and somebody else is talking in French, maybe both of us understand German, for example. So there's a translator who tries to understand English, talks in something like that. So this mediator guy, this on an X is, we need to support the versions similar to PyTorch. So they also have like V1, V1.1, 1.2, 1.3, 1.4, 1.5, 1.7. And then while doing this, we also have to be careful in what CUDA version we are using, what Nvidia drivers we are using, the Python libraries that tag along with PyTorch version 1.2, 1.3, and then PyTorch itself, of course. So then when we come to OnNX, again the CUDA version, Nvidia drivers version, the PyTorch library, Python library version, and then the OnNX version itself. Then if we move on, for example, if we take the framework of deployment to be TensorRT, that has 8 different versions. So all these versions sound like a small problem, but this has thrown problems that we couldn't solve for a long time because a layer here has no support here. If we establish a support here and then we go there, there's no support there. A layer inside the model architecture, let's say. So all these problems, if we solve it, and then if we look back, there's another new fast model that has come out already. So if we don't have a platform that can support this variety, then there is no adapting to how quick the research happens in the world. So scenario, now we're moving on to the scenarios of how we can modify and grow this knowledge base so that at the end we will have a platform that can support this variety.
One question, sorry Ajay, just to comment on what he's saying. I mean, when we develop a model, usually during the development or designing the architecture of the deep learning model, researchers or developers come up with a new custom layer, something that is not convolution, not ReLU, not whatever, pnorm, it's not a fully connected layer, it's something new, so that it is not actually supported in the baseline of the PyTorch, which already includes lots of library, lots of different types of layers, but it is very, very common that people that they are working on the like edge of the research, they come up with new things, and definitely they are not supported by PyTorch and whatever else it is in the pipeline. So that is one of the main sources of the problem.
Indeed.
To clarify.
Well, to add more to it, PyTorch has to come up with it. If not, So that's the starting point. If we don't have anything in PyTorch, then they cannot get started unless they want to define the layer themselves. But even if we have it here, having it here and here is the story that we've been talking about. So this new layer, when I mentioned, rightly pointed out by Hamid, is let's say, for example, a simple layer as transposed convolution. So we have convolution for years now, but if we change the problem slightly and make it into transposed convolution, which is they call it deconvolution. There are different names to it. For example, which is used from convolution goes from higher resolution to lower resolution, typically if you don't have padding. But deconvolution does the reverse. So it grows from smaller pixels to higher resolution. Higher resolution. You can do it without without deconvolution, but deconvolution is a trainable way of doing it. You can do bilinear upsampling. Example. So this small thing would not have support. This might come as a surprise to a lot of us. So then we have scenario 1. These scenarios have been broken down into where in the pipeline we have a problem. So why is that? Is because there is a way of dealing with it based on where it's identified. So if you know if it's in the beginning, if it's in the middle, if it's in the end, if it's what kind of a problem, can it be solved by another supported layer with a bunch of other layers, or can it be supported by something else? So that's what we are going to look at when I mention about scenarios. So the first scenario here is an unsupported layer in the very first, or in the very last, let's say. This we've had, all these scenarios we've had. Similarly, then replacing an unsupported layer and then retraining the, unsupported layer and then retraining the model. That's the second scenario. So when you typically replace it, maybe that layer is again a trainable layer. Now we have disrupted the way the weights have been aligned in the model. Now you have to tell the model whole new story of how to look at the images or whatever is given to the model as an input. So you have to tell the model itself a new story. Then move this unsupported layer to post-processing stage. Thankfully, if this is possible, then there's one advantage and one disadvantage. One advantage is that you can smoothly put it in the end of the pipeline, train the leftover, and then only do this as a quick step at the end, or maybe not even quick. But the disadvantage is this should be more or less a non-trainable layer, let's say. If that's the way it is, then it's quite easy to handle this guy. And then implementation of the supported layers in every framework. So I've shown PyTorch, I've shown OnNX, then there's TensorRT, or if you want to choose Jeremy Mace, or you want to choose TNN, or you want to choose TensorRT. TensorRT I've already mentioned. So if you want to choose any final deployment framework, that until that end of that pipeline, you need to have established a support for all this new layer. That's the fourth scenario. And then I can show you on a model viewer how the graph looks like in a while. Can I swap?
Yeah.
Just.
Okay, let me just. Okay.
Great. So this is how one of the models look like. So first you have the input data. And then you have a layer called add, then you have a layer called convolution, then you have batch normalization, then down and down. This is just to give you how the graph might look like. It's an entire graph of the functions for the model to understand what's the input data. So now that we have this, let's go into every scenario. What the hell? Okay. The first scenario, now we looked at the graph, right? So the graph was already modified. It started off with this subtract in the initial layer, then it turned out to be add because subtract was not supported in one of the frameworks in the pipeline. Then we replaced it with add with a negative weight. So if subtract is not supported, then you do minus of add. So that's a quick thing. This fix might not be handy for all other cases, but this was good for us. Maybe in the initial layers you have something else, maybe the convolution itself in the beginning, which is not supported, which would be really terrible. But if it's not supported, then we need to look at all the other scenarios to see what suits the best for this model. In case this is something as simple as this, then you don't need retraining. So you can just quickly go over it. Now, if you have replacing an unsupported layer, so this was convolution transpose, I was talking about the transposed convolution, deconvolution, and maybe something else that we know of. Then we have to convert that layer into a layer that's of support, convolution, reshape, transpose, reshape, then come back to this pipeline of argmax. So these are a bunch of different layers with which we can bring in the functionality of transposed convolution. Then if we do this, we have to do this retraining. So tell the model the whole story of how to look at the images, because now my responsibility has changed as a model itself. Okay, let's start from the beginning. So or maybe not too much from scratch, but you still need to do some retraining. And then the unsupported layer to post-processing stage. So there is, let's say, this transposed convolution, for example, or after convolution, you need to take this this guy out. You can do this. You can do this whole graph inside the training pipeline, and this guy as an external Python file, let's say. So you can combine these two guys to get your desired output. This graph will be built on the fly at the end of the pipeline. So then functionality would be another file to call and then merge with the established model. So this is also a nice scenario where you can take it out, where the last segment of the pipeline is not a trainable layer, for example, let's say. This requires a bit of retraining. This is a critical case where, because until here the model would have predicted that down below some guy is taking care of whatever we've learned. But now that is being replaced, there could be a little bit of difference in accuracy. So it's safe to train, but in this particular scenario, maybe you might not even have to train. But yes, the fourth scenario is implementation of this unsupported layer from PyTorch version 1.1, 2, 3, 4, whatever you have, then to OnNX, then to TensorRT, and then you're done with this, provided you've addressed your CUDA, Nvidia drivers, and your libraries, Python libraries, whatever you use. But beware in mind that at the end, you might not even have the executable might not run in an environment where it has Python support even. So it's typically maybe C or C++ at the end. So you need to find a suitable substitute for whatever you want to run at the end. So those are all different things, but if you are implementing an unsupported layer, then and then you want to retrain it, you need to have access to data, which in the other scenarios was also the case, that you need data for the cases where you have to retrain. But it would be nice if we don't have to train it from scratch. Now we can show.
Yeah, I think if you click one more.
Okay, yeah. Oh, sorry. Yeah, now we are about to show you. Was there a question, gentlemen? From you? Okay. No, I can play.
Okay.
It's good enough. So here, what we are trying to show is how we develop. So forget about what's displayed. It's just some print statements to see what's working and what's not. Is an example of one particular model that we wanted to move from the development to deployment. And this is how it looks like. Oh man.
Okay, wait.
No, this is. Great. So we are trying to run the model inside Nvidia Xavier, something a little bit bigger than this. to comply GDPR, let's say. So this is what we want to do. I hope you don't know the person behind this. So
It's not me. Yeah.
somebody else. But so, this is a very nice use case. Let's say if you want to move to an edge device. Why is that so? Because if you want to do this on your cloud, or like the other gentleman who pointed out, if you want to do it on tensor processing unit or over the cloud, there's some latency and you need offline video to do this. Or you can send the videos right from the device to there and then get it back. So you need to get hold of the data. Instead, if you can do this, imagine if you can do this with your edge device. If you can do this, you don't have the cloud communication, you don't have to give your data to somebody else. You can prevent a lot of things, including your cost. So that cost, AWS, TPU, GCP, Google Cloud Platform, whatever you're trying to do, this is going to be an endless cost that you will pay until the very end, right? If you port it to an edge device, if you can do this real time like we are doing, this entire unit is upstairs, but we couldn't do the demo because we needed a connection to it. We couldn't make it. But if that edge device is given 3 connections, one is power supply. If you want to monitor, then you have to attach it to a display. If not, internet connection, or not even internet connection, valid network connection. So it could be within the devices inside of a car, so connected things, right? So if that is there, then this can run real time. Let's see how the cost differs. So, okay. If you take, for example, need 3.5 euros an hour, is it too small or can you guys see this? Great, thank you. So per hour, and then you have like 20 patrolling cars, which has this camera mounted on them. Okay, let's forget about this. If you have 20 cars that's running around the city of Lyon, each of which that has 7 cameras or even 10 cameras, that's typically how it's done. So it needs to look at the front, sides, back. You need a ton of different cameras. So let's assume it's 7 on the car, and then we're patrolling for 10 hours. Then you need to send this whole thing for 1 day onto the cloud, store it somewhere, and then do the processing. So the fee is, the processing machine alone takes a fee of 3.5 euros an hour. And if you do this is just for 1 day, and this is also a closed case. It's not magnified as how it's going to happen in the industry. Every now and then you might see somebody going on the streets with this camera mounted on top of them. It's a real use case. If according to GDPR, we don't like our faces to be stored somewhere, our personal details to be stored somewhere. So to avoid this is something the industry is facing. So something like this is preferred by the companies, because if you do this for 30 days, this already comes out to, calculators?
147,000.
Yes. Okay, thank you. If that is going to be the cost, an edge device with this AI capability, little bit of maintenance to it, or however you want to do it, that would be much cheaper than this. Maybe the initial cost is a little higher, but it will pay off on the longer run. The second month already is profit. Third, fourth month, it's just going to run on and on. So this is how magnified it is. So 140,000 a month, and that happens recursively. So to put this down, we need to have a framework. We need to have a platform that can do this deployment and take us all from research to our edge devices and similar such cases. It could be drones. It could be finding hunters. It could be for a million other reasons, like I discussed about the applications of it. So now, given all this story of why we need to do deployment and what are the problems involved in it, one trivial step, one very important step in this is this model optimization. And let me hand this over to Hamid.
Okay, thank you, Ajay.
Thank you.
So I don't know if anyone has any questions until now. Then I will continue. So with that said, now we know having an optimized model is important to us. And why is this so? Because sometimes the cost is really important and the first factor. It is always a factor, but sometimes is not the major factor. But sometimes we need to have an optimized model because we need it to run faster. Maybe that is the first objective. For some use cases, for instance, if we have a camera which it has to operate like an object detection or something, it has to operate on a higher frame rate than a limit. And if the model is not optimized that much, and sometimes we have a quite complex model which basically runs in a device very slow. So we have two solutions. The first is that we just run it in a very much more powerful device, which is just simply inefficient, and it comes with more costs, but then we will be able to meet that requirements and operate it on a higher FPS. But the second is that try to optimize the model. And by optimizing the model, we mean many things, including increasing the utilization of the hardware itself. And that's why the model optimization is very, very important. And what are the typical model optimization approaches? We will discuss. What are we expecting after optimizing the model? What are the SDKs and libraries available to optimizing deep learning models? So this is just briefly explaining how the process is going on. So let's start from here. We again are in the research and idea environment, and then we come to the development. So once we have everything, we want to productize and also deliver it to the customer. These are two of the latest works that we have done in this. One is actually this one, which has been presented in DST conference this year, and also this is the other one which we discussed about the model optimization. So we can have multiple techniques, which I will explain in more detail, like quantization, network pruning or compression, parameter clustering, TensorRT conversion, model porting, and that can be, of course, for any kind of model, like classification, detection, segmentation. And then we also optimize them based on the hardware, make it energy efficient, memory efficient, and also building an engine like TensorRT for Nvidia devices, and then we will make it ready for deployment, and it becomes much, much more optimized. So let's see what model optimizations usually offer. By model optimization, we mean to offer higher throughput and faster inference process. We usually, with the computer vision, we discuss about frame per second. So an optimized model can offer and operate in a higher frame rate. We also mean by having more efficient memory access and data movement, because in deep learning, one of our main sources of energy consumption, and also in many cases the performance bottleneck is because of the data movements, and also moving lots of data from the main memory to the GPU or the computing elements. That is simply because we cannot have enough caches on chip in order to support all the parameters that the deep learning has. And then because we cannot fit that, we cannot exploit any temporal locality. Then we also mean by saving overall energy consumption. So whatever it can also result in saving energy consumption, even if it is not resulting in very much more FPS, it can be considered as optimization. And also sometimes the optimization is with the purpose of having the model smaller and more compressed. When we have a smaller model, the model simply becomes much smaller. It occupies less space in the memory, and also the memory transactions consequently become less. So we are talking here about two different ways of optimization. First is hardware-dependent optimizations, which we optimize the model for a specific hardware. And the second is that some approaches can be hardware-independent. So regardless of where the model is going to be deployed, we can optimize by some means. So let's discuss about hardware-dependent optimization approaches. So the first one is that we can have like something like tensor optimization. So that is like how the operations that are going to be done, like the computing operations, can be simply optimized. Imagine that in the calculation of the deep learning, we have usually lots of multiplication additions. So as a very simple optimization is that we already have instructions that we are calling them fused multiplication addition. So that is one instruction with 3 operands. You get 2 source operands for the multiplication, and the third operand will be for the addition. And yes?
I was wondering what remains manual and what can be done automatically, because you need to model the hardware very finely to be able to do that.
Yeah, that's a good question. I would say we don't know to the best of our knowledge that something is 100% automated. We always have until now something that we have humans involved, but there can be some level of automation, by meaning that, for instance, when we do a deep learning inference or training, usually regardless of the high level, what is the layer, what is the operations, what is the tensor, if we break down that problem into a low level implementation, that will be translated into a series of matrix multiplication. So that matrix multiplication can be implemented in many ways. We will show that later. We can optimize the same matrix multiplication depending on the parameters of the matrix. This is what actually the very highly optimized libraries of, for instance, cuBLAS, I don't know, OpenBLAS, or these libraries for linear algebra are doing. So they are, depending on your architecture, your cache size, your GPU, CPU, they can run a series of tests and determine that for these dimensions, what will be the proper operations, or like breaking down the matrices into series of smaller tiles or something like that. In the end, if you put everything back, the big picture is the same. You have a matrix multiplication to perform, but the way that you do it, either you do it in a naive implementation or you break it into tiles, and then how the tiles should be break down, what should be the dimension of each tile. Either you can use the vector instructions of the CPU, or if you have an architecture that supports vector implementation like this SIMD instructions, or using multi-threading. So these are all helping to do so. But I would say at least the beginning is fully manual, but then we have some form of automation in some of these libraries, which is just running a series of tests, which can take, I don't know, hours on the hardware. And then they specify what is the best combinations for this dimension, for that dimension. They build some information, like a history of, I don't know, references. And then when you launch your code, depending on what has been experienced, they just call that sub-function in order to perform that specific operation. This is what, for instance, Nvidia is doing, or some of these libraries are doing. Yes?
So are these optimizations already part of those frameworks you mentioned before, for example, PyTorch? That is, when you write a code and you program a network,
Yeah.
and then it gets passed into the GPU, is it somehow optimized, or are you talking about like extra optimization?
Well, it is partially, but not all the optimizations that we want to talk about here are optimized, are considered. For instance, PyTorch, again, offers something like a very high-level API, and then underneath, it uses the highly optimized libraries of Nvidia, for instance, if you are targeting an Nvidia GPU to deploy, or a x86 CPU. So it diverts the implementation and calls those libraries. So in fact, they are quite optimized, but if we want to have something running on one of the hardwares that we discussed and there is no implementation for that, or we have to use other libraries, then it comes to these kind of steps.
To add to his point, and to give you a little more picture, at every stage of this pipeline, that different frameworks that we use, they will have some kind of optimization. But since they are targeted to address the generic audience, like let's say generic processing units, their optimizations are not, what we can say is we can do a little more to adapt to what you have in place. That they have not explored because they primarily orient themselves as either research frameworks. So their motive is to make it easier for researchers to get started with, define a model, run the training. So that's where they stand. And then this OnNX guy, he is in between. I want to get it from you, give it to him. That's it from my side. And the final guy is, so like the table that we saw, each one of them wants to be a master in each one of these devices, but not all of them or something. So that's where we still have some room, well, a lot of room, which comes to a surprise, comes as a surprise.
Yeah. So, for instance, multi-threading is something that you do based on your architectural support, whether how many threads you can handle and what's the best way of dividing the application into multiple threads. This is related to the hardware. Again, vectorization or using SIMD instructions is depending on the hardware, because we may have a latest Intel architecture with AVX 512, for instance, or an old Intel architecture with SSE, which is just 128 bits. Then the length of the vector determines how you want to perform vectorization, and then that affects your optimization. Like another thing is that sometimes, as I said, it is very common to break down the matrices into smaller tiles. Then that is something very important, because there is lots of factors coming into consideration, like the size of the caches, your memory interface, and a lot of other things that determines whether you can break down into more smaller blocks and then you bring them into the CPU, or you can make it into a larger number of or larger size of the blocks. Another important thing is that improving the data access pattern. For instance, sometimes you may see that a simple multiplication of matrices can, I don't know, give you a specific cache miss rate. And if you can somehow reorder your data to explore more temporal locality or reduce the cache miss rate by some extent, this can be very beneficial and it can improve your performance. So here we want to show you that, for instance, what will be the outcome of these steps. This is from I think the Apache TVM that we use. For instance, we have first the naive implementation of two matrices which we want to multiplicate, and then we do blocking by just making the matrices into small blocks. We do vectorization, we do loop permutation in order, I mean, like loop unrolling, and then array packing and some parallelism, and this is just the result. You see that the baseline execution time was around 3.5 milliseconds. Then when we started blocking, we got a lot of improvements. And then with vectorization on that specific CPU, not that much. But then we combined everything with parallelism. We see that it is like, I think around 35x, as far as I remember, smaller or even more. This is the same operations, so nothing changed. The output of both the baseline and this is exactly the same, but this is much faster, and this is in the CPU. We have the same thing. For instance, I just referred to Kutlas, which is an open source equivalent of Nvidia Kublas. So this is a bit misleading. We have CUB LAS, which is the closed source library of Nvidia for linear algebra. And we have Kutlas. This is again by Nvidia, but this is open source. And it is, according to my experience with this library, it can offer very close performance to Nvidia closed source library. So you see that what they are doing is actually, I just recorded some video here. So you see that they break the matrices into small tiles, and then they do some fine-tuning of these tiles, what should be the size of the tiles, and then they will do this. So you see that this is the naive implementation of the matrix multiplication, which is definitely very inefficient. And then they make here the operation is in tiles, and then they consider these things. Okay, this should be coming to the shared memory, and then the memory comes to consideration. What should be the best combination of this thread block size, the number of warps, number of thread blocks, and these are the things that, for instance, we have different implementations in a library like this, depending on what is the size of the input and output matrix, and the output it is very much faster than the naive implementation. So this process is very different, because for GPU implementation we have lots of other things to consider compared to CPUs. Then now we move to the approaches that are actually hardware independent. So what do we mean by hardware independent? It means, for instance, we have the weights or parameters of the model. There are lots of works that they have offered to cluster the parameters. So for instance, we have all the weights in floating point values. What will happen if we just specify 256 or 128 different clusters? Then we only need 7 bits to index to any of these 128 clusters. Then inside the cluster we will have a 32-bit floating point centroid, but we only need 7 bits in order to index which cluster we are referring to. This is a very well-known technique. Probably hundreds or thousands of works have done that with the purpose of optimizing the model. And that is simply just reducing the size of the model, because imagine that you have 4 million parameters in a model. Each of them acquire, like, for instance, 4 bytes, because they are 32-bit floating points. Then that will be 16 million bytes. If we cluster them, we just need 8 bits in order to index those. So it's like a 4x reduction from the size, because we don't need the 32-bit anymore. We can just use 8 bits to index them. This is one technique. We have quantization. For instance, it is very well known that the FP32 is maybe too much in terms of precision for representing deep learning models. And if we use a lower precision arithmetic like FP16, The results and experiments in many works show that it provides the same identical output as the FP32, because still with FP16 we have enough precision to capture the complexities of the model. People even went much beyond that, and it is now very common to have int8 or even much lower than that in order to represent the models. And it is so popular now that in Nvidia devices we have hardware support for int8. And the latest GPU architectures, they are already having hardware support for int8, for FP16, which we didn't have before, and still we don't have in many architectures. For instance, in CPUs, as far as I remember, we don't have any support for int8 because there is no justification. But for deep learning, there is very much use case for having that. Another important optimization, which is again hardware independent, is to prune the model. So it is very well known that a model can be pruned, by meaning that lots of connections and nodes can be removed from the model, and model still be able to provide its functionality in some cases without even any accuracy loss. Lots of works have shown that you can prune the model up to 40 to 50% without any accuracy loss. And then if you prune more, you start to see performance degradation in terms of accuracy. And what are the benefits of pruning is that you just reduce the number of computations and also reduce the size of the model, because if you remove some connections, then you don't need to store them. In some cases, it can result into a sparse matrix, which cannot get that much performance, because you have to do that sparse matrix multiplication. But there have been lots of solutions or accelerators which they can simply exploit the sparse matrix and sparse operations. Some works also show that you can have up to 90% or even further pruning, but in order to maintain the accuracy, you need to retrain the model, so that when you lose accuracy with that retraining, you recover that accuracy loss. And then you will be able to prune more, and then you do retraining, and then you prune more, you retrain. And that process continues until a point that even with the retraining, you cannot maintain your accuracy as the baseline. And then you simply stop there. So another very important objective for model optimization is to save the energy consumption. And we will say how this can affect the energy consumption. So as I said earlier, lots of energy is consumed because of the data transfer. And this is very much the case with the mobile devices, which the computing energy is much less. We have very high, ultra low power computation units. And the dominant part will be the memory. But reducing the memory transactions by, for instance, pruning, or by using quantization or data clustering, can result in significant reduction in overall energy consumption. Techniques, again, like quantization, clustering, the pruning, each in different ways can offer the same thing. Note that some of these techniques can be combined together. For instance, we can prune the model and still do quantization, so we get much more benefits. It doesn't necessarily mean that we have to just use one of these. We can prune the model and also we quantize it, and we get further improvements. We can do quantization. For instance, if we simply go from FP32 to FP16, we just reduce the size of the model by 2x, and from FP32 to int8, we just reduce the size to 4x, and that is a lot of savings in energy and data transfer. And this is not only the case, but we have some scenarios that the memory can be a bottleneck. And if the memory is bottleneck, when you reduce these, you sometimes resolve that bottleneck, and then you can get even beyond 2x or 4x performance improvements, because then you don't have that bottleneck which was there before. And that is quite happening with complex models, or when you are running it in a hardware that you have not that much good balance between the computation power that you have and also the memory bandwidth that is available to you. Especially with devices like, for instance, Nvidia's system on chips now, we have one chip which has the CPU multi-core, it has the GPU, it has accelerators, the deep learning accelerators, and all they are sharing a DRAM, a low power DRAM. And that can sometimes, if you manage to utilize and engage all those computing elements, then the memory can definitely become a bottleneck. And these kind of techniques can simply reduce the pressure on the memory, and then you get a lot of benefits. We have other techniques in order to also reduce the overall energy consumption. For instance, batching the model. For instance, batching means that you want to infer a model. Instead of having one image, you somehow merge or put 8 of them or 16 of them together, and then you do the inference for that batch of images. And where the benefit is coming from, the benefit is that when you fetch some of the model parameters and you keep it in your computing element cache, like the CPU or GPU cache, then meanwhile it is there, you can use that for 16 images. Otherwise, you have to do these operations for one image, and then you don't have enough cache to explore temporal locality, and then you have to fetch all this data again, and that can result in a lot of inefficiency. So another technique that I discussed also earlier is the data reordering in order to improve the cache locality. This is a very important thing. Sometimes transposing a matrix can result in a much higher cache hit or something like that. Similar to what we have discussed, these techniques can compress the model or reduce the size, like the quantization can result in reduction of the model size. We said that just using FP16 can give us 2x reduction in the size of the model. Pruning can also reduce the size of the model. So you see that some of these techniques affect in many directions, like they directly affect the energy consumption, they directly affect the size of the model, and also improving the performance. Clustering the model parameters can provide up to 8x reductions. There have been lots of works that they have shown that even you can use only 16 clusters, which for that you need 4 bits in order to do some inference with basic models, or in some specific domains like speech recognition or problems that the complexity is not that significant, and you will be able to capture the complexity with these kind of things, and also some other tricks together. But this is pretty feasible, and it has been done before. So now I think this is our last slide.
Yes.
And we are quite on time.
So now we are heading towards the conclusion. This is the last slide. What we are now trying to say is from research to deployment. That's where the issue is. And let's try to solve it with a more generic platform that rapidly evolves with this knowledge base. So what we've recorded in this paper is just a small portion of what we've done in the lab. There's much more to what we have in our experience, and also we can have a lot of collaboration to make this possible to grow this knowledge. So every new stuff that comes in every now and then is hosted here, and this one platform, let's say for example, you drag and drop stuff, you say where I want to go, the endpoint, what device I want to target, and then you're done. So it's not that easy, but to build this, it takes time. But if it's there, then nobody's going to use very old stuff. Like I mentioned, V1 is not going to be there in your phone. Say, why is this important is, as a consumer, let me say, all those gentlemen and ladies who are using mobile phones right now or after the conference, whatever, your data, using your laptop, surfing the web, your recommendation, all this is being done elsewhere. Some of us would complain that I need to retain my privacy. Most of us would agree with that. Some say let's contribute to the open source, but for the for the biggest segment of the population, if it's a concern, then how do we retain the positives of this? Meaning, how do I still get my YouTube recommendations but not lose what I'm watching, not give the data away? Or yeah, so something like that. So that's why, as a consumer, we need this platform. Why do we need this as a business, let's say? We need this because I've shown with some calculation that right from the initial stage, what Hamid was showing is like 3 ms, 3.5 ms to 1 ms. This improvement, this speed up, would translate here for a business as tens of thousands of dollars here, or euros here. That is for a business. So we've targeted the consumers, we've targeted the business for research. So now I want to develop this model. If I have this transportation or porting capability, then I don't always go ask my institution for an account somewhere else, do stuff there to know if it's going to work, if it's not going to work. If it's going to be a tiny hardware that I can buy with a couple of €100, then we're done. A lab gets 10 of it. So researchers, developers, consumers, and businesses can benefit from such a platform where we want to have, where we're trying to build. This is a huge dream that we have here, but we're trying to build a web interface that makes this feasible. So drag and drop your model after converting it into whatever unified file that you target or you're comfortable using. Then that dropping would already enable you with a story of where it can go. So this and this are the list of hardwares that you can target, and then you'll get the best of performance in a matter of a few minutes, let's say. Then the engine is created, you port it. So then the platform will have its own pipeline of how it goes through, list being mentioned by Hamid. He said different compression techniques, different hardware dependent techniques that we can employ. So this pipeline will have all of it. And we can have multiple services within this platform as well. One of which we just saw that blurring your face. Another could be something else. Another could be identifying the employees entering, or maybe identifying if somebody is sick due to COVID. All these applications could be translated as a service and taken out of this platform as just one engine file or one executable file. You put it in your mobile phone or in some edge device with a camera, put it in front of wherever you want to detect, and then it's going to do the job for the next 10 years. That's typically the lifetime of a Nvidia device, but next few years. So that's your play toy from now on, let's say. So this is what we are trying to do as a dream. And one step towards it is the introduction we gave now. And let's hope we get there. And I hope you guys enjoyed the session. Thank you, guys. And
thank you very much.
No questions.